Hi and welcome to this MicroTasker Shorts video where we'll be taking a look at the MicroTasker I2C Slave Bootloader. We start by taking a look at how to configure the MicroTasker Serial Loader project. In config.h I find the board which I'd like to operate on. In this case it's the Freedom KL02Z board. Although it's not necessary for the I2C loader, I'm also going to enable this serial interface so that we have an S record loader. This makes it a little bit easier to see what's going on. And finally I enable the I2C operation. Now opening loader.h, I'm going to set the I2C slave address. Here we have a 32 setup, but we want to use 50. Since I'm going to be building using the GNU makefile, I checked that the configuration is correct for this processor. First thing I do is make sure that we have the Cortex M0 Plus core and not an M4. And then at the bottom of the file I check that we're using the correct linker script file. Here I change it to the KL32-4 because our processor has 32 kilobytes of flash and 4 kilobytes of RAM. This means I'm ready to build. Here we see the GNU post-build execution taking place. And this is the completed build.
What I have here are two Freedom boards. This one is the Freedom KL02Z board and this is the Freedom K64F board. The two are connected together via two cables, which is the I2C bus between the two. This is the master, this is the slave.
This diagram represents the configuration where we see the Freedom K64 board acting as an I2C master and also having a local slave application image which we will then transfer to the slave device. Since both of the Freedom boards have an OpenSDA VCOM connection on the UARTs, we can now connect debug terminals to them. Here we see the debug terminal to the Freedom KL02 board, so when we make a reset to this board with the bootloader loaded, this is what we see. Notice that the flash is initially empty. We also connect a debug terminal to the Freedom K64 board. When this board is started, this is the menu which we see, and when we go into menu number 7, which is the I2C menu, we have a load command. I'm going to do first of all a load to a non-existing I2C slave address to see what happens. Here we see we had no response. So now I'm going to repeat, but using the correct address, which is 50 hexadecimal. Here we see the loading process, and here we see that after the loading is completed, the slave device restarts and now we have an application operating. I have a command in the application which allows me to reboot back to the bootloader. Now I'm going to repeat the process. And again we've reprogrammed the device. The difference between the two loading operations was the first one loaded without really requiring to delete the slave's flash memory because it was already deleted. In the second case we didn't have a deleted application, and so the master device did have to delete the slave's flash. As we can see here, that took a little bit longer. What I'm showing here is a logic analyzer recording of what just took place. Immediately we see that there are actually two parts of the operation. The first part here, which looks a bit different to the second part. The first part is when we are deleting the slave's memory, and this is where we're programming the new program to it. This shows some interesting features of the I2C bus. So the first thing we're going to do is to take a look at what happens when we start communicating. Full details concerning the protocol can be found in the serial loaders document. But what we see here is that the first command that the master is sending is a write command to the address 50. It's sending a command 1. Now the command 1 means please delete your flash. That means the application flash. We have another 2 bytes, 52 and 84. These are just keys to confirm that we really wanted to do this operation. Now, following this, the master is now starting to poll the state of the flash in the slave device by doing reads. Here we see a read of 51. Now, there's a break in the operation of the bus here, which I'll come back to in a second, but we're going to look at the next byte, which is a 1. Now, this is the version number of the I2C Slave software. And then if we look at the next byte which is being read, also after quite a considerable delay, again I'm going to get back to that in a minute, we see that then we have a 0. That means we have Slave bootloader software version 1.0, and continuing, the final byte is a 0. We know that it's the final byte because we have a NAC. That means that the master does not acknowledge the final byte, so that the slave then understands that the complete transfer has completed. The 0 means that the flash at the I2C slave device, the application flash, is not yet deleted. So what's happening in fact is that the master device is polling the slave, asking it all of the time, tell me what is the state of your internal or your application flash. And now I'm going to get back to these very long delays here. How do we explain that? Well, the fact is that when the slave device on the I2C bus cannot respond to a message, here it cannot respond to the read taking place because of the fact that it's in the process of executing the command, which was to start deleting the flash. Deleting the internal flash takes a certain amount of time, and during this time interrupts are blocked, and the behavior of the I2C slave is that it does something called clock stretching. What it does, it holds the clock line low. That tells the master that it must wait because the slave has not had the chance yet to handle the byte that it's just received. And this is quite interesting, and it's very useful as well because it's a sort of handshake protocol which is taking place right at the lowest level. And this is giving us a bit of information because it means that it actually took the slave device about 10 milliseconds to delete its first sector. The slave then continues by deleting as many sectors as are necessary to delete the complete application space, and we see here that this repeats, so it's deleting 1, 2, 3, 4, 5, 17, 18, 19 sectors in fact, which is true because I know that it's deleting 19 kilobytes, and one sector on the KL02 happens to be 1 kilobyte in size. So now we turn our attention to what happens when we start programming. So we can see a block of software being copied here. We see a write, we see the command 0, which means write to flash, and then we see what looks to be almost random data because that is the code being copied. Here we get a bunch of zeros, but otherwise it's fairly random, and we copy this in blocks. Here we do 58 bytes at a time, but the actual size of the block is not important. We can use any size we want. And after each block has been transferred, which completes here, we have a repeated start on the bus. Then we have another polling from the master, a read from 51. Now in this case the master is reading 5 bytes at a time. 1, 2, 3, 4, 5. The meaning of the status information during programming is different. The first one means everything is okay, we're in the programming cycle because it's giving us a 0, 1. Afterwards we get a counter value 0, 0, 0, 3A. This is the amount of data which the slave has already received. So the master can send a block of data, poll its status just to make sure that everything is in order, and also that the slave has really received the amount of data which we expect. This is repeated until the master has sent all of the slave information, and the very last thing that it does is commands a reset. Here is the last polling to check that everything was okay. Now, because the master has now sent all of its program, it sends the write with command 2, which is reset, with 55AA just as an extended key, just to make sure that we really wanted that command to be executed, and that's when the reset that will then take place, and the slave device then reboots. Many thanks for watching this video, and good luck with your own work using the uTasker I2C Slave Bootloader.